G'day mathletes, welcome back to Mathematics for another free HSC maths lesson. Today's focusing on extension 2, looking at a bunch of HSC revision questions relating to the vectors topic, which usually tends to lean towards a lot of high level questions in the HSC. So we're going to go through a variety of bands, starting off with some easier ones and then finishing off with some pure hell from some E3, E4 level questions. So before we get into it, just a quick run through of what I mean by these bands. So when I say we're looking at an E2 question, it just means that students who answered these correctly were typically scoring between 50 to 70% overall and above. So the high level questions are the E4. We're going to be going through a couple of these at the end, so stay tuned. Okay, let's dive into an E2 level question from the 2023 HSC. We're finding the angle between two vectors given. It's worth 3 marks and we're answering to the nearest degree. Now, this is a very straightforward question, but they've typically been chucking one of these in HSC every year, so definitely recommend you know how to confidently work through a question like this because it can be a very easy 3% of your exam. So very similar to what we study in extension 1, finding the angle between two vectors using our formula given on the reference sheet in case you forget it. So to find cos theta, all we need to do is take the dot product of A and B and divide that by magnitude of A times magnitude of B. So just like with all these questions, if you're already familiar with vectors and you want to get the most value out of these questions, always best to pause the video once I've gone through the question, have a crack yourself, and then when I go through my solution, it might be the same as yours, or if you get stuck, then at least having a go first will make these questions more meaningful for you. Okay, so let's dive in. Let's start off by finding the magnitude of A. So the way we find the magnitude of a vector is we take its x, y, and z components, and we square them, we add them all together, and we take a square root. We're essentially just doing a bit of three-dimensional Pythagoras here. So we've got 1 squared plus 2 squared plus negative 3 squared. And that inside our square root works out to be 14. So the magnitude of A is the square root of 14. We'll do the same thing for B, and taking negative 1 squared plus 4 squared plus 2 squared. Summing those all together gets us a value of 21, which means that the magnitude of B is equal to the square root of 21. And now the last piece we need is the dot product, which is nice and easy. We just take our x components and multiply them together to get negative 1. Take our j or y components and multiply them to make a. Multiply the z components to make negative 6, and then just combine these all together. So minus 1 plus 8 minus 6 gets us a value of positive 1. Okay, so putting all three of these values into our formula, it looks like this. We have cos theta, where theta is the angle between the two vectors, is 1 over the square root of 14 times the square root of 21. Now to figure out theta, all we need to do is apply inverse cos, so arc cos, shift cos. You can combine your two square roots together if you prefer, but that's completely optional. But from now on, it's just going to be a bit of calculator work, and chucking that into your calculator should get you an answer of approximately 87 degrees. So all very straightforward, and like I said, a nice and easy 3 marks get us started off for this video. Okay, moving on now to an E3 level question, a multiple choice from 2023. So I'm really focusing on recent HSC questions for these videos, so they're new to the ones that are already in my extension 2 playlist. We have the equation of two lines given, L1 and L2, and we have 4 options. Either these two are the same line, or they're parallel, or they're not parallel, and we want to find out where they intersect. Okay, so to work through this question, you need to know the structure of a line equation in vector form. The way we read this line equation is this is the equation of a line passing through the point negative 1, 2, 5. So it goes through this point, and it's in the direction, or it's parallel to, the vector negative 1, 3, 1. So just think about it as the first point is what your line goes through, and the second vector is what your direction is, or what you're parallel to. So if we want to see whether these two vectors are parallel, we need to compare their two direction vectors, which is negative 1, 3, 1, and 1, negative 3, negative 1. Now, if these two are parallel, it means their direction vectors will be scalar multiples of each other. And what do you know? If you take this, this vector down here, 1, negative 3, negative 1, and you multiply all these values by negative 1, you get the values over here because the 1 turns into a negative and the other 2 turn into a positive. So we can show that the direction vector of line 2 is equal to negative 1 times the direction vector of line 1. This is us showing that they are scalar multiples and therefore they are parallel. So if they're parallel, we can cross off options B and D because B and D say they are not parallel. So it's got to be A or C. So now that these two lines are parallel, either they are parallel and they don't intersect, or they're parallel and they're going through the same point, which means they're the same line. Because if they're parallel and they go through the same point, has to be the exact same line. So let's see if they go through the same point. Let's take the point that L2 goes through. L2 goes through 3, negative 10, 1. Let's use a bit of algebra to see if line 1 also passes through the points 3, negative 10, 1. The way we do that is we set our line 1 equation equal to 3, negative 10, 1, and we see if we can find a value of lambda that makes the equation work. So we're going to split this into 3 little separate parametric equations, and I'm just going to start with the easy one down the bottom. 5 plus lambda times 1 is equal to 1. Okay, so taking all my z components and making a little equation. Now if I solve this by taking 5 off both sides, I get lambda equal to negative 4. So let's see if making lambda equal to negative 4 works for the other two values. Let's check the first equation. Negative 1 plus lambda times negative 1. But now lambda, as before, we said it's going to be negative 4. So negative 1 take away negative 4 is negative 1 plus 4. And negative 1 plus 4 is equal to 3. So it works for the first equation, okay? And if we wanted to check the middle one as well, it would work. 2 plus negative 4 lots of 3 is in fact equal to negative 10. So what we're seeing is that when lambda is equal to negative 4 in this first line, the output is the point 3, negative 10, 1. So this is showing us that, what am I doing here? 5 plus lambda, I've already done that. Anyway, I already did that one. I don't know why I did it twice. I should have done the middle equation. What I'm trying to say here is that when lambda is equal to negative 4, line 1 outputs the point 3, negative 10, 1. And so we've shown that line 1 passes through a point that line 2 also passes through. And because they're parallel, that means they must be the same line. So A is your correct answer for 1 mark in 2023. Okay, up next, we have a 2024 question at the E3 level. We have a point A with a position vector of 8, negative 6, 5. And we have a line L that has this equation given by this. Okay, so we have point B lies on a line L and has position vector P, P, 2P. Show that line AB magnitude squared is equal to 6P squared minus 24P plus 125. Okay, that's our first part. Let's make a little space so we can work through this. Now, if we want to find a line AB, in vectors, we can do AB is equal to B minus A. So this is a very common result in vectors. So to figure out an expression for the line AB, we're going to do position vector B, which is given by this, and we're going to subtract position vector A, which is up here. So we're going to say AB is equal to P, P, 2P as your B vector, subtracting your A vector, which is 8 minus 6, 5, and combining these two together, we get P minus 8 for our top component, P plus 6 for our Y, and 2P minus 5 for our Z component. Now, this is an expression for the line of the vector AB. We're going to do the magnitude of this, and we're going to square it and hope that it looks like this thing given here. So to take the magnitude, once again, we are going to take our 3 components, our X, Y, and Z, and we are going to square them, and we are going to plus them together, and then we're going to do a square root. So this expression is the magnitude of AB. We want to do magnitude AB squared, so if we square both sides of this, it's going to get rid of the square root on the right-hand side. So what we're going to do next is we're going to square both sides of this equation, and while we're doing that, we may as well expand out all our brackets using a perfect square expansion. So the square root's gone, and we have P squared minus 16P plus 64 for the first bracket. For the middle bracket, we have P squared plus 12P plus 36, and for the last bracket, we have 4P squared minus 20P plus 25. Okay, and now on the right hand side, if you collect all your terms, so we put the P squared with the P squared and the 4P squared and etc., group everything together, and you do end up with the target, which is 6P squared minus 24P plus 125. So that's why this is only 1 mark, because, was it 1 mark or was it 2? Let's check. It was 1 mark. Yeah, it wasn't heaps of work. Part 2 is a little bit more for 2 marks, but here is our solution for part 1 once again. Okay, now we have that, we can move on to part 2, which is hence or otherwise, come back. Hence or otherwise, determine the shortest distance between the point A and the point on, between the point A and the line L. Okay, so point B lies on the line L, and we've already got an expression in part A for the distance from A to B. So actually question 1 is already done for you, the expression of the shortest distance from A to B. Okay, so here's our expression. A is a point and B is on the line. So the distance between A and the line is given by part I. So we're really just trying to find the shortest possible value of AB, which means we're trying to find the shortest possible value of AB squared. So interpreting all this, all we need to do for 2 marks is figure out what is the value of P that makes this quadratic have its lowest possible value. And for a concave up quadratic, because it's got P squared, if you're trying to find the minimum point, you're really just trying to find the turning point. So we're going to try and find the minimum value, aka the turning point of this parabola, which gives us our distance. Okay, AB squared is the distance. Okay, so to do that, we can just do a little bit of differentiation. We can take the first derivative and turn this into 12p minus 24. And now if you want to find a stationary point or a minimum or maximum value, you take your first derivative and you solve it equal to 0. So 12p minus 24 equal to 0. Quick and easy solve gets us p equal to 2. And so this tells us that when p is equal to 2, the parabola given by this equation here is going to have its lowest possible value, which means AB squared will have its lowest possible value, which means AB has the lowest possible value, and AB is the distance between A and a generic vector on the line L. So it's a big concept question with a very small amount of algebra. So to finish it off, we're just going to put in P equals 2 into our 6p squared expression over here. This gets us the distance of AB. So if we just take the square roots, it'll get rid of the squared, and we have our distance AB. So, so we have 6 times 2 squared minus 24 times 2 plus 2125. That's distance AB squared. So we'll just take the square roots, and then this in red gets us a value of the square root of 101 units as our minimum value. Okay, beautiful. Let's now start to get some geometry involved and kick up the difficulty again. This question has some E3 and some E4 components, and it's from the 2024 HSC. And if you've been studying past papers, you'll see questions like this with pictures and lots of mumbo jumbo pretty much every year for the last 5 or 6 years. So let's dive into it. Let's try to at least. Okay, so we have the point P lying on OA. So OA is reading on further. OA is vector A, and the ratio of OP to OA is 3 to 5. All they're really saying here is that the length of OP is 3/5 the length of OA, which kind of looks like it in the picture, even though these are always not to scale. Similarly down here, from O to B, which is vector B, given the question, it says that OB to OQ is 1 to 3. That just means that if you take the length of OB and you triple it, you get the length of OQ. So yeah, OB is 1/3 of the length of OQ. R is the intersection point of a bunch of stuff in the middle. T is chosen so that OR and T are collinear. So if it looks like a straight line on this, it probably is a straight line. Okay, PR is equal to KPQ. So that just says that PR is some number times PQ. So PR and PQ are also on the same line because you take PQ, you multiply it by something, and you get PR. That's all that's saying right there. It's just a little hint to help you with the question. Okay, part I, show that OR, so vector from O to R, is given by this expression here. So we're trying to turn OR into a vector equation involving A's and B's. And A is from O to A, and B is from O to B. So let's think about OR. OR is the vector from here to here, so we can make that by doing OP plus PR. Okay, OP plus PR is equal to OR. Now we just need to try and find a way of turning these blue and green vectors into something involving A's and B's, which is pretty tough. Part 1 and part 3 are pretty tough. Part 2 is a bit easier, but yeah, this is definitely a tough question. So bear with me. It's hard to do on a PowerPoint, but I'm doing my very best for you guys. So let's dive into it. So OR, as we said, is equal to OP plus PR. Now OP is nice and easy because we said before that OP is 3/5 of the length of OA. So we can just write that. OP is 3/5 of the length of OA. Now the hint in the question was that we can change PR to be some multiple of PQ. So we've changed PR to be KPQ. Now what do we do with PQ? The vector from P to Q, a really important concept for this question, and a lot of these vector questions, is that if you want to find an expression for the vector from a starting point to an end point, a way you can get that is you can do the vector at the end of the end point, take away the start point. What I mean here is that vector PQ can be found by doing OQ take away OP. Okay, it's the same logic as vector from A to B is B minus A. We're doing the same thing here. So we're going to say that vector PQ is OQ take away OP. Okay, why have we done that? Well, because OQ we have some information about. OQ is 3 lots of OB, so it's 3 lots of B. And OP, as we already said, OP is 3/5 of OA, so it's 3/5 of A. So we've translated the entire thing now into an expression involving A's, B's, and K's, which was the goal. We just need to expand, simplify, and collect to make it look like the target to get our 2 marks. So we expand out the K with the -3/5 A. I'm going to put that at the front. So I put all the A's together, and on the end we have the 3KB. Okay, now out of these two, just taking out a common factor of 3/5 and a common factor of A leaves us with 1 minus K. So we have 3/5, 1 minus KA. That little tilde is meant to be underneath the A. I apologize, that shouldn't be there. So sorry, you get what you pay for at Mathematics, as we always say. And on the end, we have 3K times vector B, and that is the target. So that's 2 marks done for part I. So let's set that aside and let's feast on part 2. Okie dokie, part 2 is show the value of K equals 1/6, and they've told us that AR is equal to something times AB. So where's that? AR is something times AB. That makes sense. Given that H is a real number, it can be shown that OR is equal to this. Okay, so we've already figured out they have given us an expression for OR in the question involving H, and we don't need to prove it, which is good. In part I, we also established this value of OR, and we have 2 different ways of writing the same vector equation. We have 2 expressions for OR. So if these are both valid, it must mean that our X components are equal and our Y components are equal, or A and B in this case. And that's really the only trick to this question, is just setting up your 2 equations, one they've given to you and one they gave to you in the first part, but we also figured it out ourselves. And now we're just going to say, all right, these are the same thing. So that means that 1 minus H has got to be equal to 3/5 of 1 minus K. Okay, so X components are equivalent and our Y components are equivalent. H is equal to 3K. And now we just have a pair of simultaneous equations that we can solve to figure out what K is. So let's take equation 1, and we can change H to be equal to 3K. So now the right-hand side is 1 minus 3K. Now we've just got a quick and easy little equation to solve to get us our 2%. So we're just going to multiply the 5 across to the right-hand side. We're going to expand out the brackets to make 3 and minus 3K, and we have 5 minus 15K on the right. Let's add the negative 15K across to the left to make a positive 12K, and let's take the 3 off both sides to get equal to 2. Now we just divide by 12 and we get K is equal to 1/6, and there's our 2 marks done and dusted. Now we're on to the really mind-numbing part, which is part 3. Find the equation of vector OT in terms of A and B. Okay, so let's start off with our expression for OR. Why do we care about OR? Well, because if you look, OR is just some multiple of OT. So we've just spent 4 marks working with the equation OR, and now we're trying to find OT. So of course, what we've already done is going to be important. That's how these questions are set up. So we can say that vector OT is vector OR times something. There's some scale factor making it a little bit bigger to get it to be OT. So that's where we're going to start. We know what K is. We've got that out in part 2. And we're going to say, all right, vector OT is something times OR. We can get an expression for OR because we know what K is now. So we can sub in K equals 1/6 into this. And so we have 3/5 of 1 minus 1/6 for the X value. And for the Y value, we have 3 times 1/6. Both these calculations work out to be a half because we get 15 out of 30 at the front and we get 3 out of 6 at the back. So both our coefficients of A and B are just a half, and we can factor that out the front. So half out the front. Here's our expression for OR. I'm just going to put a lambda in front of it. I don't know why I picked lambda. I think it's probably just what people do. They like to get Greek letters involved, but lambda is the scale factor that's turning OR into OT. And so this is our expression for OT. Okay, so setting that aside, now we're going to need to get an expression for OT in terms of some different vectors so we can figure out what lambda is. So to do that, we're going to say OT is equal to OA plus AT, using the same trick from before. We're going to say OT is OA plus AT. Now, OA is good to go. We know that OA is just equal to vector A, so that's good. We need to figure out an expression for vector AT. And again, we're going to use the fact that, as was given to us in the question earlier, AT is a multiple of the line AQ. The reason that's good, so I'm just going to write AT is something times AQ. The reason I care about AQ instead of AT, because AQ is a vector that has starting and end points that I can work with. The start point of AQ is the vector OA, which I know information about, and the end point of vector AQ is the line from O to Q, which I know information about. I know it's 3 lots of vector B. So I have up here is A, I I have down here is 3b, which means that AQ is equal to 3b take away A. And that's how we're going to figure it out. Okay, so AQ is equal to 3b take away A. Okay, now we can just expand this and put the A's together and put the B's together. So we have negative mu A out the front, and we have 3 mu B on the ends. Taking the A's out of these two, we have 1 minus mu A, and then we have 3 mu B. So what do you know? We've just figured out two different expressions for the vector OT. We've got one that we figured out from an earlier part, and we've got the second one we figured out by doing a bit of geometry with some lines using vectors we can work with. Just like in part 2, we now have two different expressions for the same vector, so we can figure them out by doing some simultaneous equations. The A components must match, and the B components must match. So setting that up, that's a spoiler. That's meant to be the last line. Let's just pretend that's not there yet. So we have lambda over 2 is equal to 1 minus mu for our x components. And we have lambda over 2, which is the B component of the first one, is equal to 3 mu. So there's our two simultaneous equations. There's our x components equivalent, and there's our y components equivalent. Or A and B, x and y, same thing. Okay, so how are we going to solve these two simultaneously? We are going to we're going to divide the 3 across the left-hand side to get an expression for mu, and say mu is equal to lambda divided by 6. Now we can substitute that up into equation 1. So we have lambda over 2 equals 1 minus lambda over 6. And now we're just going to solve this little equation. So if we solve this, we can add the 1/6 lambda across the left. And so when you combine these two, you get 2/3 of lambda. Now we just times the 3 across and divide by the 2. So we get lambda is equal to 3 over 2. Putting that back into up here, we have lambda is 3 over 2. When you divide that by 2, you get 3 over 4. And that's why the spoiler is here of OT being equal to 3/4 of A plus B. And that's your answer for 2 marks. So like I said, very tough question. Very few students getting the E4 level in this question in 2024. But hopefully if you watch these videos, maybe you'll be getting up towards that level in 2025 and beyond. Okay, that was pretty hectic. Let's just take a quick rest break before we go into the last two questions, which are both E4 questions. Now's probably a good time to tell you, while we are just catching our breath, that these videos take me many hours to write and animate and record and edit. So I'm obviously not doing this for the money, because this channel makes me virtually no money. So I'm really just doing it because I like helping people, and hopefully these videos are helping you. If they are, and you appreciate them and you want to see more, easy way of supporting the channel is just to make sure you are in the minority who are subscribed, as opposed to the people who aren't subscribed. So helping the channel grow lets me help more people, and this just makes me happy, I guess. All right, enough about me. Let's finish off the last two questions. This one is from the 2024 HSC again. It's a multiple choice, but it's a real bastard for 1 mark. We have 3 unit vectors. That's important. A, B, and C in 3 dimensions, and we're choosing them so that A and B are perpendicular, B and C are perpendicular. And the angle theta, which is the angle between A and A plus B plus C, is as small as possible. What is the value of cos theta? So this is an absolute dog of a question from NASA, because this is going to take a lot of working out, and it's only going to get us 1 mark. So these are the questions I would leave towards the end of the exam if you have time for. Otherwise, it's better off guessing and spending your time on other marks, where working out is going to get you some marks. But anyway, let's dive into it. Let's get rid of the answers. We don't need those. Let's figure out what's going on here. Here is our angle between two vectors equation. The two vectors we're working with, however, are A and A plus B plus C. So we're going to change it to look like this. We have A dotted with A plus B plus C on the top, and on the bottom our two magnitudes are given by this. So the goal here is to get some expressions for the top and bottom of this fraction, so we can figure out what's going on with cos theta. Because we're trying to find the angle theta between these two vectors is as small as possible. So what happens to cos theta when your angle is really small? Let's take a look at the graph. As your angle goes closer and closer to 0, you can see cos gets closer and closer towards its maximum value, which is equal to 1. So for this question, if we're trying to find the smallest possible angle theta, it really means we're trying to find the largest possible value of cos theta. So the goal here is to figure out what can we do to make this fraction be as large as possible. Okay, so let's get into it. Let's start by doing the top, which is the dot product of A and A plus B plus C. If we expand out our dot product, we have A dot A A dot B, and A dot C. Now this is good because we know that because A and B are perpendicular, that the dot product of A and B is going to be equal to 0. Okay, that's known knowledge that perpendicular vectors, perpendicular vectors have a dot product of 0. And on the end we have, what do we have? A and C? We don't know. Let's figure it out. So we're using this result as well. This is very useful for a lot of vector proof questions. The dot product of a vector with itself is equal to the vector's magnitude. That's going to be super important for this question. So for the first part, where we have A dot A, we can just write that as magnitude of A squared. In the middle, A dot B is equal to 0 because they're perpendicular. And on the end, we don't have any information about A dot C yet. Okay, now what's good is it said that A, B, and C are all unit vectors. So the magnitude of A is going to be equal to 1, and 1 squared is equal to 1. So our dot product on the top of our angle formula just simplifies to 1 plus A dot C. Now let's look at the bottom, which is a bit of a tough one. Why are we doing this? Anyway, we have, why are we doing this? Oh, sorry, we're doing this because we're trying to get an expression for the magnitude of A, B, C. This is going to make sense. I forgot what I did. So using this bit in purple, but using it backwards, we have a vector squared is equal to its own dot product. So the magnitude of A plus B plus C squared is equal to A plus B plus C dotted with itself. We want to get dot products involved so we can use unit vectors and we can use perpendicular vectors. Now, this is going to be a bit of a hectic step here, but this is what happens next. When we do A dot A, we can write that as magnitude of A squared. When we do B dot B, same thing, magnitude of B squared. C dot C, magnitude of C squared. And then in the middle, we're going to have A dot B and B dot A, and then B dot C, C dot B. So we're going to have these dot product pairs of AB, BC, and AC. These are all going to happen twice when we do the whole expansion out. I didn't have room to do it, and I was feeling lazy, so you'll have to trust me that when we expand and simplify this dot product, we get this expression here because a vector dotted with itself is its squared magnitude, and we get a lot of pairs happening. Okay, this is cool because A, B, and C are all unit vectors, so these are all just equal to 1. In the middle here, we have a similar result from before where A and B are perpendicular, so this is 0. And we have B and C are perpendicular, so this is 0. So we have, next line, we have 1 plus 1 plus 1 plus 2 lots of 0, 0, and A dot C. So this bottom part turns into 3 plus 2 dot C. Okay, so this is an expression for the magnitude of ABC squared. So if we take the square root of this part in red, it's going to be our expression for the magnitude of A plus B plus C. So putting that all together now, we have the top, as we figured out, is 1 plus A dot C. On the bottom, we have magnitude of A, which is 1, and we have the magnitude of ABC, which we figured out to be the square root of 3 plus 2 multiplied by the dot product of A and C. Okay, now to figure this out, we don't have any information about A dot C, unless we start to think about the angle between vectors A and C. So let's do that. The dot product of A dot C, just rearranging our vector formula, is equal to magnitude of A times magnitude of C times cos of the angle between them. So A and C are both unit vectors, so these are just 1s. So we end up with A dot C is equal to cos alpha, because these are just 1s, like I said. Now, if we're trying to find the maximum possible value of this expression here, the maximum possible value of A dot C is the maximum possible value of cos of this angle, and cos is never larger than 1. So the maximum of cos alpha is equal to 1, which means the maximum of A dot C is equal to 1. Putting that into our expression over here, it gives us the largest possible fraction, which is 1 plus 1 on the top, and on the bottom we have 1 times the square root of 3 plus 2 times 1. Like I warned you, this is a huge amount of work to get 1 mark. So not a very good multiple choice question in my books, but they don't pay me to write exams. They just pay me to teach people to do them. So our maximum value of cos theta, which is going to be the minimum angle value, is 1 plus 1 on the top, and on the bottom we have 3 plus 2 times the square root of 1. And that is equal to 2 over root 5, which is equal to one of the 4 options, and that gets you your 1 measly mark for this Band 6 E4 level question. Okay, and to finish off what is already, I'm sure, a very long video, here is a E3, E4 level question that I think looks a lot harder than it actually is, and it's from the 2021 HSC. I believe in that year this was the second last question on the exam. So parts 1 and 2 are not too bad, but part 3 really made me think, and I had to really work around, try and get to the target here. Anyway, we have a point that lies on a sphere with radius 1 centered at the origin. Using the position vector of P, OP is given by this, and the triangle inequality or otherwise show that x plus y plus z with their magnitudes is greater than or equal to 1. Okay, let's dive into it. So let's start off by talking very quickly about what the triangle inequality is. The triangle inequality states that if you take the sum of the magnitude of two numbers, this will always be greater than or equal to the magnitude of the sum. Okay, so splitting up a absolute value into two separate absolute values is always going to make it, it's going to make it bigger. Okay, left-hand side bigger than right-hand side. So how can we use that? We're going to start off by taking our three magnitudes, x, y, and z, using the x, y, and z given to us in the question. So we have xi, yj, and zk. Now, if we want to combine these together, because we don't know anything about the individual components, what we do know is that if I combine these three together into one absolute value, point P is on a sphere with radius 1. So I know that the length of OP is equal to 1, but I don't know what the lengths of the individual components are. Luckily, we can start to combine some stuff. So like I said, if you take two vectors that are doing an absolute value or a magnitude, and you combine them together into one, you make it smaller, which means if we take this left-hand side and combine these two together, so putting the x and the y together, we've now made the right-hand side smaller than the left-hand side. Then we do it again. We take this vector and combine it with this vector and put them into one absolute value, and we've made it even smaller again. So this is our argument for the left-hand side being larger than the right-hand side. Now this is good because, like I said, we've combined this into one vector now. We know what the length of x, y, and z altogether is because this is vector P, and this is on the sphere with a radius of 1. So we know the length of this vector is 1, and that's how we get our target of having x, y, and z greater than or equal to 1 using the triangle inequality. Okay, on to part 2, which again looks hectic, but it's actually not too bad for 3 marks. Given the two vectors a and b, show that the magnitude of all the things times together is less than or equal to this and this. Okay, so this question is all just a game of do you recognize what's going on here? On the left-hand side, when I say a1 and b1 together, a2 and b2 together, and a3 and b3 together, that reminds me of the dot product because we take, x's, y's, and z's, multiply them together and plus them together. Okay, so left-hand side to me looks like the magnitude of the dot product. And on the right-hand side, I've just got the two magnitudes. I've got the square root of a, a2, a3 all squared and summed. So the right-hand side is magnitude of a multiplied by magnitude of b. So let's explore that. The dot product, as I said, is x components, a1, b1, and then a2, b2, and a3, b3, all summing together. So keep in mind that the dot product can also be expressed as the magnitude of a times the magnitude of b times cos theta. Okay, this is our rearrangement of the angle between two vectors equation. Now this is good because we're looking for a magnitude of a and a magnitude of b next to each other because they're right here. So let's change them. Magnitude of a is equal to this, and magnitude of b is equal to this. So we've almost got there. We've got the left-hand side as the dot product. We've got the right-hand side is our angle formula, just written out to make it look a bit more confusing. And we have cos theta on the end. Now, keep in mind that now if we want to make it look more like the target has the left-hand side taking an absolute value. So let's do the absolute value of both sides. Luckily, the square root terms are always going to be positive, so we don't really need to take the absolute value of these because when you absolute value something that's positive, it doesn't really do anything. So we just need to absolute value the cos theta on the right-hand side. Okay, now to finish off and get it to our target, we just need to think about what is the magnitude of cos theta. So cos theta is a wave. It oscillates between -1 and 1. If you take the absolute value of this wave, it takes all these negative parts and it flips them up. So the absolute value of cos theta is always going to be greater than 0, but less than 1. So what's happening on the right here is we have two square root expressions, and we're multiplying them by something, which is going to be at most 1, but it's probably going to be making it smaller. It's going to be between 0 and 1. If you take something and you multiply it by something that's 1 or less, you're making it smaller. So the right-hand side is smaller than the left-hand side, and that's why we have, the absolute value of this less than or equal to our two terms times together, because the cos value making it smaller. Okay, so now we can move on to part 3. Finish off for today. Using, as in part I, point P, X, Y, Z lies on the sphere of radius 1 centered at the origin O. Using part 2 or otherwise, show that X plus Y plus Z in magnitude is less than or equal to square root of 3. Okay, so here is our result from part 2, and we are trying to use this result to explain why this is less than or equal to root 3. So, it'd be really great if I could find two vectors that I could use in this equation that are going to make the right-hand side work. I looked at this and I was like, okay, cool. So I can use 1, 1, 1 for one of my vectors, because then that's going to get me, 1 squared plus 1 squared plus 1 squared, which is 3. So I get the square root of 3. But what do I do with the other one? And it took me a long time to realize that the trick here, which makes this a band 6 question, is yes, one of the vectors we're going to use is 1, 1, 1, because that does lie on a sphere of radius 1. And the other one we're going to use to make the left-hand side give us these absolute values is we're going to take vector B as the magnitude of X, the magnitude of Y, and the magnitude of Z. Okay? So by taking these values, we are still creating a vector which is, on the sphere, but it's just very cleverly trying to insert these values into the equation to make the left-hand side look like what we need it to. And that right there is the trick that I couldn't really figure out for a long time, but now I know it, so hopefully I'll be aware of this next time. Okay, so using my A and B, we're going to do the left-hand side is our magnitude of dot product. So we have 1 times absolute value of X, we have 1 times absolute value of Y, and we have 1 times absolute value of Z. That's all inside a big absolute value around the outside. And for our magnitudes, we have the 1, 1, 1, as I mentioned we were looking for before. And we also have the magnitudes of X, Y, and Z being squared, plus together, and then square root. So it's kind of like we're doing the magnitude of a magnitude, which is a very strange concept, but it gets us 2 marks on one of the hardest questions in the hardest HSC exam. All right, so let's proceed. On the left-hand side, we just get the absolute value of X, Y, and Z all plus together inside another absolute value. We get a root 3 here, and when you take the magnitude of X and you square it, it's the same thing as just doing X squared, okay? Because either X is going to be positive and give us a positive answer, or X is going to be negative and give us a positive answer. So squaring makes the absolute value redundant, and that's why we can leave them out of our expression here. And we just have that one there. Okay, now to finish off, what are we trying to make? We're trying to get rid of everything going on here. Well, on the right-hand side, we have the square root of X squared plus Y squared plus Z squared. This is the length of a vector, P. And as we've already established, P lies on the sphere of radius 1, which means that the length of P is equal to 1, which means this expression here is just equal to 1. So we can get rid of that off the right-hand side because it's just 1. When you're doing the absolute value of a bunch of positive things plussing together, you don't really need it. If you have like 2 plus 3 plus 5 absolute value, the absolute value is doing nothing to your answer. So because the left-hand side, everything inside the absolute value is positive and plussing, it's not changing your answer anyway, so we can just get rid of the outer absolute values, and that's how we fudge our way to 2 marks to explain why X, Y, and Z magnitudes plus together are less than or equal to root 3. Okay, that was a bit of an experience after a 5-period day at school, but hopefully somewhere in those ramblings you got some more confidence working with vectors and a bit more awareness of the kinds of bands and levels that are expected in the HSC. So yeah, if you made it to the end, bravo, you're very brave. Thank you for watching, and I'll see you for some more extension content very soon. Bye for now, not forever.